Yes, in the previous file, we have discussed the theoretical part of the dimensional analysis topic, where we understood units and dimensions, what is principle of dimensional homogeneity. Then dimensional analysis can be done by two different methods. One is Rayleigh's method and another is Buckingham's pi theorem based on the number of variables. So, we also understood them. Now, in this topic, we will discuss some examples on Buckingham's pi theorem. Also, we will understand what is similitude or model laws, as well as some dimensionless numbers. So, I will directly go into page number 6. Okay. Now, before we discuss the Buckingham's pi theorem, here I have discussed about similitude and model laws. So, when you want to analyze a big or a structure like maybe a ship, then constructing an actual ship and then doing some case studies or experiment on this may be always a costly affair in terms of manpower, energy, finance required and all those things. So, what is done is a model is constructed. Model is a miniature version of the actual one, which is also known as prototype. But to construct a model, some rules have to be followed. That is, the model and prototype should be geometrically identical, kinematically identical and dynamically identical. Based on this, we have these similarity laws. What do you mean by geometric similarity? It says that if P is denoting prototype here, M is denoting model, dP by dm or LP by LM must be a scale ratio. That is, whether you follow a scale ratio or not decides whether your model and prototype are matching or not. So, if I reduce the diameter by 4 parameters, then length has to be reduced by the same parameter. Similarly, AP by AM can be written as L into B divided by L into B for model, it becomes L square. So, scale ratio should be followed. Similarly, kinematic similarity indicates the ratio of Vp by Vm, that is velocity of prototype by velocity of model, should bear a velocity ratio. More about this you can always go through the text. Next, in the dynamic similarity part, it is also known as the ratio of force. So, when model and prototype follow the geometric, kinematic and dynamic similarities, it is said that the similitude exists between the model and prototype. So, you should be able to write a short note on this similitude and model analysis. Next, in this analysis, what are the different types of forces that we consider? So, the forces that are considered in the analysis are, we have inertia force Fi, known as rho into A into V square, viscous force is Fv, mu into V by L into A. So, all these the equations written on the right hand side are the final values. So, except 3, 4, 5 and 6, first two have some steps in between. So, how it is finally rho A V square, kindly go through the text either R.K. Bansal or K.L. Kumar. Next, gravity force is Fg, rho into A into L into G. Pressure force is converting pressure into force by multiplying by area. Surface tension by multiplying by length. Elastic force is K into L square, where K is the elastic constant. Now, these forces when okay, now we have some dimensionless numbers. Dimensionless itself indicates that there are no dimensions for them. They are the numbers, but these numbers play an important role in the analysis. The first dimensionless number we have is the Reynolds number. Reynolds number is the ratio of inertia force to viscous force. Inertia force is rho A V square, viscous force is mu into V by L into A. Finally, we get rho V L by mu. Sometimes when it is used for a circular pipe, we also call it as rho V D by mu. Now, the units of rho V D together is same as the unit of mu, so it is a dimensionless number. Similarly, next Froude number, it is a ratio of under root inertia to gravity force. You can see that common thing is inertia force is there in the numerator everywhere. So, dimensionless number 1 is 1 by 2, dimensional number 2 is 1 by 3, like that. So, if you remember the 6 forces in series, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6 directly give you all these numbers. It is just a shortcut to remember them. There is no other particular relation. Next, Euler number is the ratio of inertia to pressure force. So, under root rho A V square by P into A, you will get V divided by root of P by rho. For the second one, you will get V by root of Lg. Similarly, Weber number is inertia to surface tension force, V by root of sigma by rho L. Last one, Mach number is the ratio of inertia force to viscous force. Finally, you will get V divided by root of K by rho. Later in the unit number 5, we will prove that K by rho is nothing but the velocity of speed. So, it is C. So, Mach number is also known as velocity of the object to velocity of the sound. So, there are no numericals on these dimensional numbers, but we need to have an understanding of all this. More about these numbers will be discussed in the topic called as heat transfer, as well as the fluid machines, that is turbo machines. So there more about these numbers will be discussed. Right now we are using only Reynolds number in unit number 5, where we discuss laminar flow and viscous effects. So some problems are solved here. So the pressure difference delta P or pressure gradient is found to be a function of diameter of pipe, length of flow, velocity of flow, coefficient of absolute viscosity mu, and density of fluid rho. Now we have to find a relation between delta P and the remaining parameters. When you are asked to find a relation, you are forced to use all those rules, but when you are asked to prove something, you can indirectly find which are the repeating and non-repeating variables. So here I will write a function of delta P dl v mu rho is equal to 0. So 6 variables, 3 fundamental units, so maximum 3 pi terms. So which are the repeating variables? So there are 2 variables of diameter and length as velocity geometric parameters. We will select D. Both v is the only parameter related to kinematics, no issues. Next, for dynamic parameters we have rho, mu and delta P. Delta P cannot be selected. Between mu and rho is simple, so we will select rho. So when D, v, rho becomes repeating variables, the remaining delta P, L and mu becomes non-repeating variables. So I will associate delta P with pi 1. So I want to write pi 1 as a function of pi 2 and pi 3. So when I write d raised to a1, v raised to b1, rho raised to c1 into delta P for pi 1, now I have to solve for pi 1, pi 2, pi 3. Before that I will prepare a table where I have written the units and dimensions of each and every variable. This should be correct, then only your problems or solving for pi terms will be correct. So when I solve for pi term, even if someone has confusion between what is the unit of pi, please remember pi is a dimensionless number. So it is m raised to 0, l raised to 0, t raised to 0 is equal to d raised to a1. D is measured in length, v velocity is meters per second, lt raised to minus 1 b1, rho is kg per meter cube, m l raised to minus 3 c1 into delta P. Please remember the non-repeating variable will not have any constant as a power. So when you solve for pi 1, you will get pi 1 as delta P by rho v square. Similarly, when you solve for pi 2, where again pi 2 is m raised to 0, l raised to 0, t raised to 0, you will get as pi 2 as L by D. When you solve for pi 3, you will get pi 3 as mu by rho Vd. Now you can write pi 1 as a function of pi 2, pi 3, or delta P is equal to rho V square into a function of L by D and mu by rho Vd. Exactly the function cannot be known by using this theorem right now, but by experiments the exact function, that is delta P is equal to rho V square into L by D into mu by rho Vd, can be found out. There are similar problems related to this which already have listed earlier. All those problems can be solved by applying this principle of dimensional homogeneity as well as solving for pi terms, that is using Buckingham's pi theorem. So I request everyone to go through all these problems. So here we conclude the discussion on dimensional analysis. Some of the problems which are most commonly used, I request everyone to go through is efficiency is a function of density, viscosity, weight density, diameter and discharge. So neta is a function of, final solution you will get is neta is equal to a function of mu by rho omega d square into q by d square omega. Please remember that phi is a symbol for function here, okay, not, it is not any other parameter. So repeating are d omega rho and non-repeating are neta, mu and q, and remember efficiency has no units. Next, velocity is a function of rpm, that is n, diameter of d, not rpm, it is h, d, mu, rho and g. So obviously the repeating variable are h, g and rho, and non-repeating are v, d, mu. Please see in the second problem, you are not asked to find something, you are asked to prove that v is equal to root of 2gh into a function of d by h and mu by rho vh. So by common thing you can see that h is there, h becomes one repeating variable, g is the only parameter defining the kinematics, so g is the repeating variable, and among dynamic parameters we have rho and mu. As we discussed earlier, rho should be selected because it is a simple term. So like this, sometimes by looking at the end solution you can select which are the repeating, non-repeating variables. Please remember, in this problem which is already solved in Archibonsel book, pi 3 you will get initially in a different value, you will not get mu by rho vh, but if you divide that third variable by pi 1, what you get finally is mu by rho h. So detailed steps are available in the textbook. Please go through this problem. Third problem, the hydraulic power P is a function of weight density, velocity, diameter, viscosity, density and C, where C is a constant. So you are supposed to find the relation using dimension analysis. So select dv rho as repeating, remaining as non-repeating. You will have 7 terms, so obviously there will be 4 pi terms. So you can easily solve this. Just whatever the steps you apply for solving for pi 1 is to be extended for pi 2 and pi 3. So all the principles, the principle of dimensional homogeneity, solving for a1, b1, c1, or equating the powers of m, l and t, everything remains the same. Next, the torque T is a function of diameter, rpm m, n, coefficient of absolute viscosity mu, and density rho. So you are supposed to find a relation here. You can see m is 5, n is 3. So there are 2 pi terms. Select d and rho as repeating variable, t and mu as non-repeating variable. Remember, t is the dependent variable, should never be a repeating variable. So you will get pi 1 as t by rho n square d raised to 5, pi 2 as mu by rho n d square. So when you have only 2 pi terms, a function of pi 1 pi 2 equal to 0, or pi 1 is a function of pi 2. So t by rho n d raised to 5 is a function by mu by rho n d square, or t is equal to rho n square d raised to 5 into a function of mu by rho n d square. This is another problem. And last one, the pressure gradient is a function of dl v mu rho. I think this is already solved with all the detailed steps. Like this, any problems having number of variables, maybe 4, 5, 6 or 7, can be easily solved by principle of dimensional homogeneity and Buckingham's pi theorem. So at least solve problems where at least number of pi terms are minimum 3, or at the most 1 or 2 problems where number of pi terms are 4. So with this we conclude the second topic of unit number 4, that is dimensional analysis. This is the second file discussing only the numericals. In the earlier file already we have discussed the theory part.